Today we are putting away the aesthetic mood boards and grabbing the calipers, you could say,
Yeah.
because we are diving deep into how high-quality garments are truly engineered. This isn't just about fashion, it's really about material science and, well, rigorous testing.
hmm
We've compiled sources detailing 7 absolutely critical best practices. These are used by the world's most respected apparel brands.
Right.
Our mission today is to show you exactly how product developers move beyond simply designing clothes to engineering durability. It's kind of a roadmap for ensuring quality compliance, building serious brand reputation, and slashing those costly production failures and returns.
That's the key distinction, really. When you, the consumer, buy a garment, you're trusting the brand to have already done that engineering work.
Exactly.
True quality is invisible until it fails.
Right.
And the sources make it clear that preventing that failure begins way back, at the foundational level. Selecting and crucially validating materials. Okay, let's unpack this, starting right at the beginning of the supply chain. Mandatory testing.
Right, that initial state, let's call it the pre-production quality audit, it seems absolutely non-negotiable.
It is.
If you're sourcing fabric or materials, the first engineering gate requires you to get physical performance test reports from your suppliers before you confirm any major order. Like, no test, no trust.
Exactly. This isn't some handshake agreement. It's a demanding technical checklist. And think about the specific performance metrics they actually demand. For instance, colorfastness.
Yeah.
It's way more complex than just checking if the blue fabric fades in the sun.
Right, it covers bleeding, when dyes run in the wash, and that dreaded crocking.
Oh, yes, crocking.
Crocking is when color transfers onto another fabric just through friction, often dry friction.
Right.
Like, imagine wearing a dark denim jacket and having blue stain the seatbelt or maybe your white purse.
That's a classic quality failure, a
Yeah.
big one. And equally mandatory is testing abrasion resistance,
Okay.
particularly for those high-stress, high-friction areas like inner thighs, underarms, cuffs. If the knit or the weave breaks down too quickly there, the garment just looks worn out almost immediately.
Oh, yeah. We've all had that sweater that instantly starts looking, well, ratty.
Mm-hmm.
And if the garment is knitwear, you have 2 extra mandatory enemies to fight. Pilling. That's resistance to forming those small, annoying balls of fiber, and spirality.
Spirality. Now that's a fascinating engineering problem, quite unique to knit constructions.
Really? How so?
Well, it measures the fabric's tendency to twist or curl after washing. You know when you put on a t-shirt and suddenly the side seam is running diagonally across your stomach?
Oh, yeah.
That spirality failure dramatically impacts how the garment hangs, and it completely ruins the fit.
So that's why my favorite vintage bandit now seems to be trying to rotate 45 degrees around my torso every time I wear it.
Yeah.
It's not just me. It's physics.
It is entirely physics, and textile engineers have to counteract it. They adjust the tension, the construction of the knit itself. But what's often overlooked in this initial testing stage, even the tiniest components, the trimmings, require separate physical and chemical validation.
Trimmings, you mean zippers, buttons, labels, like everything that's not the main fabric.
Exactly.
But why spend so much time validating a tiny metal rivet? Seems like overkill.
Because quality is measured by the weakest link, isn't it? And a failed trimming guarantees a dissatisfied customer. For mechanical things like buttons and zippers, you need a pull test.
Okay, a pull test.
Yeah, to ensure they meet minimum tensile strength standards so they won't just rip out of the fabric. But for metallic items, like snap buttons or rivets, corrosion resistance is mandatory.
Wait, a tiny metal rivet. Corrosion resistance. Why is that mandatory if it's rarely exposed to the elements, like rain?
That's a great question, and it really shows the depth of the engineering thought process here. They aren't just thinking about rain. They're anticipating residual moisture from laundering, maybe harsh chemicals and certain detergents, and importantly, the high saline content of human sweat, perspiration.
Oh, wow.
If a rivet rusts prematurely just because of body moisture, that rust spot will permanently damage the fabric around it, so they have to withstand the actual wear environment.
That level of detail is intense.
Okay.
Okay, so moving past initial testing, we get to the actual construction phase. This is all about engineering durability, identifying and reinforcing those weak areas.
Absolutely. The design process itself has to anticipate failure points. The fabric might be sound, but every point where one piece meets another or where strain is concentrated, that's a high-risk area.
Right.
The sources specifically point out shoulders and necklines in knitwear, for instance. They're just prone to stretching, warping, losing shape, the classic failure point for so many casual tops.
Okay, so here's where the technical solutions come in to save the day. How do engineers structurally reinforce, say, a strecky neckline?
Well, you specify very precise reinforcement techniques. One key solution is applying stay tape.
Stay tape.
Yeah, it's a non-stretch, low-profile tape. It's sewn right into the seam line, typically along the shoulders and necklines of knit garments. It basically acts like a tiny tensile cable, providing stability where the knit structure might otherwise stretch out of shape. It solves that problem of a shirt neck getting wide and sloppy after, 5 washes.
I see. It's like putting rebar into concrete, basically.
Kinda, yeah. A good analogy.
What about other high-stress areas, like pocket corners or belt loops? Those always seem to go first.
Right. For those zones prone to tearing, engineers mandate bartacks.
Bartacks, those little dense stitch lines.
Exactly. Those dense little zigzag sections of stitching, maybe just a quarter-inch long, that reinforce the seam where the most dynamic pressure is applied. They're mandatory for preventing pockets from ripping away from the main fabric or keeping a belt loop from pulling free. Small, low-cost solutions that dramatically extend the garment's life.
Makes sense.
And you also specify stronger seams, like welt seams or bounded seams, for critical points in high-end outerwear or trousers. You're ensuring the construction itself is strong enough to handle constant movement and stress.
Okay, so we've sourced tested materials, we've engineered the design to resist strain. The next crucial step must be communicating the maintenance requirements clearly to the user, right? Which brings us to the third practice, effective and clear labeling.
That's right. And this connects the quality engineering directly to the consumer experience. Because if a durable garment is washed incorrectly, the consumer blames the quality, not the care instructions.
Good point.
So the source material stresses that instructions have to be concise, use standardized symbols, and offer specific recommendations.
Like those helpful notes, wash with light colors or dry flat to prevent stretching, those aren't just arbitrary suggestions, are they? They directly address the color fastness and dimensional stability issues we were just talking about.
Precisely. They're mitigating the risk of failure that the consumer unknowingly introduces through care. And the sources noted a subtle but important detail. The label should also be used to encourage eco-friendly washing practices,
Oh, interesting.
like washing in cold water, which often doubles as a quality preservation tip anyway. Cold water preserves dyes better and prevents excessive shrinkage.
That's smart, integrating sustainability with durability. Okay, so once the design is locked, labels are printed, the quality mission shifts from engineering to execution. Let's look at the fourth practice. Strict testing throughout the production process. You can't just check materials at the start. You have to monitor the factory floor constantly.
This is where control really enters the picture. It requires basically a 3-phase inspection process to ensure defects are caught before they become big, expensive problems.
Okay, tell us about those phases.
So first you have initial inspections. These focus on the bulk raw materials, everything that arrived in the factory after those initial supplier reports were approved. You're making sure they match the specs before a single piece is cut. Rejecting defective fabric here saves thousands.
Makes sense. Phase 2.
Second, you run in-process inspections. This means monitoring critical production stages as they happen, checking seam allowances, making sure patterns match up correctly, ensuring stitch consistency, little checks along the way.
But the truly rigorous work, it sounds like, is that final layer of performance trials. We aren't just spot-checking finished goods. We are actively trying to, well, destroy them.
That's a great way to put it. You need to run rigorous performance trials, like durability wash tests. They aren't just washing a sample garment once. No. They simulate multiple home laundries, maybe 20, 30, sometimes even 50 cycles.
50 cycles, wow.
To assess the garment's ability to withstand repeated washing and drying. They check for color change, shrinkage, seam puckering, fabric degradation. They're the works.
Simulating 50 cycles is really the only way to truly understand longevity, isn't it?
It is.
What about real-world use, though?
Good point. That's where trials come in. Garments are given to real people to be worn, laundered, and tracked over a specified period. This catches failures that lab tests might miss, like, how does a zipper feel after 100 uses? Or how does the cuff material hold up against constant desktop friction at work?
Ah, the little things you only notice over time.
Exactly. So what does this all mean? It means ensuring the garment performs optimally in the consumer's actual life, not just under lab conditions or in the factory.
Right. Now we move to the final piece of the quality feedback loop, the fifth practice, which is learning from failure via customer feedback.
Yes, because even the most perfectly engineered garment might be misused, or it might reveal a previously unknown weakness in a specific use case. Collecting and analyzing customer feedback is absolutely crucial scientific data.
So not just complaints, but data.
Precisely. This comes through surveys, tracking social media comments, looking at reviews online, but the highest value feedback often comes from identifying common problems on returned garments.
I imagine a returned garment isn't just an expense, it's like an engineering failure report landing on your desk.
Exactly that. When a garment is returned, the product development team has to analyze the specific failure. Did the shoulder seam tear? Did the color bleed onto something else? Did the lining rip? They need to categorize these failures by type and location. Why? To prevent that flaw from recurring in the next production cycle. It turns customer complaint data directly into design improvement.
That process truly integrates the consumer right back into the quality management system. Okay, before we get to the final and maybe trickiest practice, let's briefly touch on the sixth one. Packaging and storage. Seems simple, but maybe not.
Well, while it might sound basic, packaging is really the last line of defense against damage before it reaches the consumer. The sources emphasize that garments must be protected from 3 specific risks during shipping and storage: moisture, abrasion, and soiling.
So it's not just about looking pretty on the shelf or in the box.
No, it's about material protection. Think about it. A cheap plastic bag that retains moisture, that can lead to mildew, especially if it's shipped overseas on a long journey. That could ruin entire inventories. Likewise, excessive abrasion during transit, things rubbing together, can damage delicate fabrics or prints before the garment even reaches the store. It's the final logistics hurdle that has to be engineered just as carefully as the seams themselves.
Okay, good point. Now for the final and perhaps most complex challenge, the seventh practice. This one focuses specifically on garments with high contrast fabric trims.
Ah, yes.
Right.
This specific type of construction introduces, well, exponentially higher risk because you're combining 2 different material types, often different fabrics, different dyes, maybe different weaves, in very close proximity.
High contrast trims, like contrasting piping or bindings or maybe small decorative panels.
Exactly those things.
This sounds like a quality control nightmare. You've basically doubled the chance of the materials reacting differently to stress or washing.
Precisely. This construction elevates the risk for 2 major issues at the same time. First, colorfastness. We talked about bleeding and crocking earlier. Well, imagine white piping on a navy jacket. The navy dye is much, much more likely to bleed onto the white during washing. That's an immediate catastrophic quality failure. Visually horrible.
Instantly ruined. Okay, what's the second big risk?
The second major risk is differential shrinkage.
Meaning they shrink at different rates.
Exactly. If the main body fabric shrinks by, say, 2%, but the contrasting trim shrinks by 5%, that difference in size causes severe puckering and distortion along the seam line where they meet.
Oh, I can picture that. Looks terrible.
It instantly destroys the aesthetic and ruins the fit of the garment. And this is despite all the reinforcement work we discussed earlier, like stay tape or bartacks.
And these trims aren't just used arbitrarily, are they? They're often placed in key, visible, or stressed areas. Where do we commonly see this critical quality failure point cropping up?
Oh, everywhere, really. Trims are used for finishing edges, sometimes for seam reinforcement or just decorative details. You find them commonly at the back necklines or shoulders of t-shirts, along the side seams or center back seams of jackets or trousers, on the necklines and armholes of tops, and on the hems and cuffs of bottoms.
So lots of places.
There are lots of places, and every one of those locations is subject to friction, moisture, repeated laundering. The quality control for that tiny piece of contrasting fabric has to be arguably twice as rigorous as for the main body fabric.
Wow. This deep dive has truly underscored how much meticulous effort goes into preventing even the tiniest flaw. It's quite something.
It really is.
When a brand successfully applies these 7 practices, from the pre-order testing of a single zipper pull to the post-sale analysis of a returned, damaged shirt, the results seem clear. You get superior durability, enhanced customer satisfaction, and you build a strong brand reputation based on trust and reliability.
And if we connect this to the bigger picture, this emphasis on testing, reinforcement, and analytical feedback loop, it really transforms garment production from just a creative process into, well, a demanding exercise in material science and actual engineering. This methodical, multi-stage approach is the true foundation of quality and ultimately brand trust.
This raises an important question maybe for you, the listener, to think about. Given this rigorous multi-stage testing required simply to ensure a seam doesn't pucker or a color doesn't bleed, how much more complex is the process of building and maintaining consumer trust? in a world often obsessed with fast fashion and, let's face it, instant gratification.
Yeah, that's a tough one. And maybe think about this too.
Sure.
What specific test failure, whether it's pilling on a sweater, spirality, twisting your tee, or maybe color fading unevenly, what stands out to you as the biggest breach of quality trust? The one failure that makes you instantly lose faith in a brand? Something to mull over.
Definitely something to think about.